Mineralogy is a subject of geology specializing in the scientific study of chemistry, crystal structure and physical properties of minerals. Specific studies within mineralogy include the processes of mineral origin and formation, classification of minerals, the geographical distribution as well as the utilization. History. Early writing on mineralogy, especially on gemstones, comes from ancient Babylonia, the ancient Greco-Roman world, ancient and medieval China, and Sanskrit texts from ancient India and the ancient Islamic world. Books on the subject included the Naturalis Historia of Pliny the Elder, which not only described many different minerals but also explained many of the properties, and Kitab al-Jawahir by Persian scientist al-Biruni. The German Renaissance specialist Georgius Agricola wrote works such as De Re Metallica and De Natura Fossilium, which began the scientific approach to the subject. Systematic scientific studies of minerals and rocks developed in post-Renaissance Europe. The modern study of mineralogy was founded on the principles of crystallography and the microscopic study of rock sections with the invention of the microscope in the 17th century. Nicholas Steno first observed the law of constancy of interfacial angles in quartz crystals in 1669. This was later generalized and established experimentally by Jean-Baptiste Rome de Leslie in 1783. René Justory, the father of modern crystallography, showed that crystals are periodic and established that the orientations of crystal faces can be expressed in terms of rational numbers, as later encoded in the Miller indices. In 1814, Jöns Jacob Berzelius introduced a classification of minerals based on the chemistry rather than their crystal structure. William Nicol developed the nickel prism, which polarizes light. In 1827 to 1828, while studying fossilized wood, Henry Clifton Sorby showed that thin sections of minerals could be identified by their optical properties using a polarizing microscope. James D. Dana published his first edition of A System of Mineralogy in 1837, and in a later edition introduced a chemical classification that is still the standard. X-ray diffraction was demonstrated by Max von Laue in 1912, and developed into a tool for analyzing the crystal structure of minerals by the father-son team of William Henry Bragg and William Lawrence Bragg. More recently, driven by advances in experimental technique and available computational power, the latter of which has enabled extremely accurate atomic-scale simulations of the behavior of crystals, the science has branched out to consider more general problems in the fields of inorganic chemistry and solid-state physics. It, however, retains a focus on the crystal structures commonly encountered in rock-forming minerals. In particular, the field has made great advances in the understanding of the relationship between the atomic scale structure of minerals and the function in nature. Prominent examples would be accurate measurement and prediction of the elastic properties of minerals, which has led to new insight into seismological behavior of rocks and depth-related discontinuities in seismograms of the Earth's mantle. To this end, in the focus on their connection between atomic-scale phenomena and macroscopic properties, the mineral sciences display perhaps more of an overlap with materials science than any other discipline. Physical properties. An initial step in identifying a mineral is to examine its physical properties, many of which can be measured on a hand sample. These can be classified into density, measures of mechanical cohesion, macroscopic visual properties, magnetic and electric properties, radioactivity and solubility in hydrogen chloride. If the mineral is well crystallized, it will also have a distinctive crystal habit that reflects the crystal structure or internal arrangement of atoms. It is also affected by crystal defects and twinning. Many crystals are polymorphic, having more than one possible crystal structure depending on factors such as pressure and temperature. Crystal structure. A crystal structure is the arrangement of atoms in a crystal. It is represented by a lattice of points which repeats a basic pattern, called a unit cell, in 3 dimensions. The lattice can be characterized by its symmetries and by the dimensions of the unit cell. These dimensions are represented by 3 Miller indices. The lattice remains unchanged by certain symmetry operations about any given point in the lattice. Reflection, rotation, inversion, and rotary inversion, a combination of rotation and reflection. Together, they make up a mathematical object called a crystallographic point group, a crystal class. There are 32 possible crystal classes. In addition, there are operations that displace all the points: translation, screw axis, and glide plane. In combination with the point symmetries, they form 230 possible space groups. Most geology departments have X-ray powder diffraction equipment to analyze the crystal structures of minerals. X-rays have wavelengths that are the same order of magnitude as the distances between atoms. Diffraction, the constructive and destructive interference between waves scattered at different atoms, leads to distinctive patterns of high and low intensity that depend on the geometry of the crystal. In a sample that is ground to a powder, the X-rays sample a random distribution of all crystal orientations. Powder diffraction can distinguish between minerals that may appear the same in a hand sample. For example, quartz and its polymorphs rhodymite and cristobalite. Isomorphous minerals of different compositions have similar powder diffraction patterns, the main difference being in spacing and intensity of lines. For example, the sodium chloride crystal structure is space group FM 3 meters. This structure is shared by sylvite, periclase, bunsenite, galena, alabandite, chlorogyrite, and osbornite. Chemical. A few minerals are chemical elements, including sulfur, copper, silver, and gold, but the vast majority are compounds. Before about 1947, the main method for identifying composition was wet chemical analysis, which involved dissolving a mineral in an acid such as hydrochloric acid. The elements in solution were then identified using colorimetry, volumetric analysis, or gravimetric analysis. A variation on the wet methods is atomic absorption spectroscopy, which also requires the dissolution of the sample but is much faster and cheaper than the above methods. The solution is vaporized and its absorption spectrum is measured in the visible and ultraviolet range. Other techniques are X-ray fluorescence, electron microprobe analysis, and optical emission spectrography. Optical. In addition to macroscopic properties such as color or luster, minerals have properties that require a polarizing microscope to observe. Transmitted light. When light passes from air or a vacuum into a transparent crystal, some of it is reflected at the surface and some refracted. The latter is a bending of the light path that occurs because the speed of light changes as it goes into the crystal. Snell's law relates the bending angle to the refractive index, the ratio of speed in a vacuum to speed in the crystal. Crystals whose point symmetry group falls in the cubic system are isotropic. The index does not depend on direction. All other crystals are anisotropic. Light passing through them is broken up into two plane polarized rays that travel at different speeds and refract at different angles. A polarizing microscope is similar to an ordinary microscope, but it has two plane polarized filters, a below the sample and an analyzer above it, polarized perpendicular to each other. Light passes successively through the polarizer, the sample and the analyzer. If there is no sample, the analyzer blocks all the light from the polarizer. However, an anisotropic sample will generally change the polarization so some of the light can pass through. Thin sections and powders can be used as samples. When an isotropic crystal is viewed, it appears dark because it does not change the polarization of the light. However, when it is immersed in a calibrated liquid with a lower index of refraction and the microscope is thrown out of focus, a bright line called the Beck line appears around the perimeter of the crystal. By observing the presence or absence of such lines in liquids with different indices, the index of the crystal can be estimated, usually to within plus or minus 0.003. Systematic mineralogy is the identification and classification of minerals by the properties. Historically, mineralogy was heavily concerned with taxonomy of the rock-forming minerals. In 1959, the International Mineralogical Association formed the Commission of New Minerals and Mineral Names to rationalize the nomenclature and regulate the introduction of new names. In July 2006, it was merged with the Commission on Classification of Minerals to form the Commission on New Minerals, Nomenclature, and Classification. There are over 6,000 named and unnamed minerals, and about 100 are discovered each year. The Manual of Mineralogy places minerals in the following classes: native elements, sulfides, sulfosalts, oxides and hydroxides, halides, carbonates, nitrates and borates, sulfates, chromates, molybdates and tungstates, phosphates, arsenides and vanadates, and silicates. Formation environments. The environments of mineral formation and growth are highly varied, ranging from slow crystallization at the high temperatures and pressures of igneous melts deep within the Earth's crust to the low temperature precipitation from a saline brine at the Earth's surface. Various possible methods of formation include sublimation from volcanic gases, deposition from aqueous solutions and hydrothermal brines, crystallization from an igneous magma or lava, recrystallization due to metamorphic processes and metasomatism, crystallization during diagenesis of sediments, formation by oxidation and weathering of rocks exposed to the atmosphere or within the soil environment. Biomineralogy. Biomineralogy is a crossover field between mineralogy, paleontology and biology. It is the study of how plants and animals stabilize minerals under biological control, and the sequencing of mineral replacement of those minerals after deposition. It uses techniques from chemical mineralogy, especially isotopic studies, to determine such things as growth forms in living plants and animals, as well as things like the original mineral content of fossils. A new approach to mineralogy called mineral evolution explores the co-evolution of the geosphere and biosphere, including the role of minerals in the origin of life and processes as mineral-catalyzed organic synthesis and the selective adsorption of organic molecules on mineral surfaces. Uses. Minerals are essential to various needs within human society, such as minerals used as ores for essential components of metal products used in various commodities and machinery, essential components to building materials such as limestone, marble, granite, gravel, glass, plaster, cement, etc. Minerals are also used in fertilizers to enrich the growth of agricultural crops. Mineral collecting is also a recreational study and collection hobby, with clubs and societies representing the field. Museums, such as the Smithsonian National Museum of Natural History Hall of Geology, Gems, and Minerals, the Natural History Museum of Los Angeles County, the Natural History Museum, London, and the private Mineral Museum in Beirut, Lebanon, have popular collections of mineral specimens on permanent display.